Complex analysis. 1.3. The polar form and roots of complex numbers. So far, we've shown that there are two ways of representing the complex numbers, the ordered pair way and the rectangular way. Are you ready for a third? Suppose we have a complex number z with coordinates a, b. We can see that this number can be represented in polar coordinates similar to R2. I want to focus on the angle that the position vector makes with the positive real axis. Call it theta. The imaginary part of the number, b, can be represented as the magnitude of z times the sine of theta. Similarly, the real part of z, a, can be represented as the magnitude of z times the cosine of theta. Now remember our rectangular notation of z, a plus bi. If I take my new discoveries and plug them into this equation and do a little simplification, we can see that z can be written in terms of two new coordinates. One coordinate tells you how long the position vector is, and the second coordinate tells you what angle does the vector make with the positive real axis. Now, typically, we shorten the cosine theta plus I sine theta into a notation called cis. Again, just to be clear, this is very similar to the polar notation and formation used in R2. Z tells you the length of the position vector, while theta tells you how much to rotate that vector away from the positive real axis. Now, let's go back to a question I asked several videos ago. What is the geometric interpretation of multiplying two complex numbers? I promised that I would answer this, and now that we have the polar form of complex numbers, we can see what the interpretation is now. Suppose I had two complex numbers, x and y, and let us represent them in polar form. If we multiply them together, perhaps a keen eye can notice that we can do something special with the angle coordinates. Due to angle summation identities, which I encourage you to prove on your own, cis of theta 1 times cis of theta 2 just so happens to be cis of theta 1 plus theta 2. So here it is, the geometrical interpretation of multiplication. The interpretation is that when you multiply two complex numbers, the magnitudes of both numbers multiply, while the angles add. It turns out that if you want to multiply an arbitrary number of complex numbers, say n of them, then the result is if you were to multiply all of their magnitudes together and add all of their angles together. I encourage you to prove this on your own. The use of induction would be very helpful here. We've talked about addition, subtraction, multiplication, and division. And now that we have the understanding of the polar form of complex numbers, we can start to talk about roots of complex numbers. The idea is, say that we have a complex number a. Don't let it be 0 because that would be trivial. Can we find numbers z such that the square root of a is equal to z? What about the third root of a? The seventh root? What about the nth root of a? Let's go back to the general formula of multiplication of complex numbers in the polar form. If we make all the numbers in the general formula the same, and by that I mean multiply z times itself n times, then we can do some simplification and see that z to the n is equal to the magnitude of z to the nth power times cis of n times theta. This is known as de Moivre's formula, and it holds for any value of n as long as it's an integer. So back to the original question about finding roots of complex numbers. There's another way to phrase this question that's perhaps more suggestive. And that is, if I know a and n, what are the values of z that allow z to the n to equal a? We can go ahead and expand this relationship using the new formula, as well as expand a into its polar form. This implies a possible solution to this equation would be when the magnitude of z to the nth power is equal to the magnitude of a, and the cis of n theta is equal to the cis of alpha. Just doing some algebra implies that at least one solution exists when the magnitude of z is equal to the magnitude of a to the 1 over n power, and theta is equal to alpha over n. So, plugging everything back in, we see that this is an nth root of a. However, there are more nth roots as well. If we add 2 pi to alpha, this is another nth root of a. And it turns out that if you add any integer multiple of 2 pi to alpha, you will again get an nth root of a. I should be clear here. and state to get unique nth roots, k should be between 0 and n minus 1. If you go past n minus 1 or below 0, you will begin to repeat roots. I want to do an example and use this new formula for generating roots so we can see what roots of complex numbers look like. I've chosen a complex number, a, which in its polar form is 3 square root 2 times cis of pi over 2. Just to be clear, a's magnitude is 3 square root 2, and the angle it makes from the positive real axis is pi over 2. I want to find the third roots of a. We will use the formula for computing nth roots of complex numbers. Firstly, let's plug in our magnitude and angle coordinates. And now, if we let k equal 0 and do some algebra and computation, one of the third roots of a has a magnitude of 1.618 and an angle of pi over 6 from the positive real axis. Let's go back to our formula and plug in k equals 1. Out pops another third root of a, and it has the same magnitude as before, but the angle it makes is 5 pi over 6. Again, plugging in k equals 2, the final third root has the same magnitude of 1.618 and an angle of 9 pi over 6. Now again, if we started plugging in higher and higher values for k, we would begin to repeat roots, and I'll let you think about why that is true. But in general, for any complex number, there will be n distinct nth roots. Also, the roots will have the same magnitude, and they'll be equally spaced, angle-wise, from one another. That's all I wanted to cover in this video. To really drive the understanding of what roots of complex numbers look like, I'll end this video by showing some code that will help visualize how roots of complex numbers change as the number itself changes. I'll display the square, third, fourth, and fifth roots of an ever-changing complex number. The ever-changing complex number is in light blue and has magnitude of 2, but its angle coordinate rotates around the plane. The red ticks represent the roots of the number and change similarly as the complex number changes. Hope you enjoy. Thanks for watching.